Welcome to Lyons Township High School AP Physics. Today we got a problem involving circular motion or tangential motion. And the example today, and you might want to write this down, you can pause the video. We got something on a circle. So for instance, we've got a circle going like that, like a merry-go-round, or in this case a wheel, and we're going to put something on the edge of the wheel. For instance, maybe it's an ant. And the ant's going in a circle, and he's starting from rest, and there is an angular acceleration for the wheel, so it's speeding up as it goes. And there's some other data there. We are horizontal, so we're not worried about gravity or anything like that. We're just worried about the effects of the turning of the ant. And some things that we're going to determine about the ant is, calculators. Some things we're going to determine about the ant is after this 1.2 seconds is up, okay, where is he? Like, where is he? Okay, well, we're going to say he's starting at 0 degrees. We'll call that right there. We'll say it's due east. Where is he? How fast is he going? And we'll talk about what I mean by how fast. There's a couple ways to interpret that. And then also, what's his total linear acceleration? And we'll talk about that too. So let's start with where is he? Okay, well, he is going to, we'll say he's accelerating this way, so counterclockwise. And we're going to find what angle he's at. Now, I've given you angular information, so we're going to find an angle. This is actually this first part of this is a kinematic problem. Probably the easiest equation to use for this is to say delta theta is omega naught t plus 1/2 alpha t squared. And we've got all that, so we can just plug and chug. So we've got this is 0 plus 1/2 alpha is 3 and t is 1.2 squared. So you get delta theta is 2.16 radians. Okay, now some of you probably know radians really well. For the rest of us, I like to convert that to degrees so I kind of know where I'm at. So if I take my 2.16 radians times, there is 180 degrees in pi radians, or there's 360 degrees in 2 pi, it's a full circle. But either way, you'll get approximately 124 degrees. So now I kind of know where I'm at. I am in the second quadrant, okay? Now I'm going to draw that on here. Okay, 124 degrees, well that's 0, that's 90. I have to go 34 more, so he's about there. And this angle right here is about 34 degrees. Okay, now we've answered where is he. Okay, the second question is how fast is he going? Okay, well, the first part of that would be what's his rotational speed. Now you'll notice that every part of this wheel, okay, whether it's near the inside or near the outside, goes around the same amount of time. That's omega final, okay? So we're going to find omega final for the wheel first. And that's going to be the same everywhere, including for our ant. All right, so omega final, probably the easiest equation to use for that is omega final is omega naught plus alpha t. We've got all that. This is 0 plus 3 times 1.2, and so omega final is 3.6 radians per second. So that's the entire wheel spinning at that rate at that moment, at that 1.2 second mark. Now, the other thing that you probably would want to know is if I had a speedometer on them, what would it say? So that's linear speed or tangential speed. In other words, how fast is this moving right there? Now, that changes depending on where you're at in the wheel. Something on the inside of the wheel will have a relatively slow tangential speed. Something at the outside of the wheel will have a faster tangential speed. To go from an angular quantity to a linear quantity, you basically just multiply by r. So v tangential is r omega, okay? And for us, r was 1.5 and omega is 3.6. And if you multiply those out, you get 5.4 meters per second, which is about 12, 13 miles an hour or so. Okay, so he's not moving too incredibly fast just yet. All right, the last question was, what is his total linear acceleration? Now, he is right there. He is doing two things. He has two accelerations at this moment, linear-wise. Anything going in a circle has a radial acceleration, and that radial acceleration is always inward. So he's going to have, and I'll draw it from here, he's going to have an A sub r, radial acceleration, okay? But he's also speeding up. So he's going to have an acceleration in his direction of motion. We call that tangential acceleration. That's A sub t. Now, by definition, those two are perpendicular to each other. Okay, so he's got a radial acceleration just by virtue of going in a circle, but since he's also speeding up, he has a tangential acceleration. Now, those are both relatively easy to calculate. I'll start with tangential. The tangential acceleration, and I'll keep the color coding the same there. Our tangential acceleration is simply r times alpha. So for us, r is 1.5, and alpha was given as 3, and so you get a tangential acceleration of 4.5 meters per second per second. So that's part of the linear acceleration. Now he's also got a radial acceleration, and here you got a couple choices. The equation for radial acceleration is v squared over r, or you can substitute r omega in for v, in which case you would get r omega squared. Either one's fine. I'll use the second part of this. So r was 1.5, and omega final is 3.6. And I can't forget to square that. And I get a sub r to be about 19.4 meters per second per second. Now, by the way, that's pretty good. It's about 2 Gs, about twice gravity. Okay. Now, to find your total acceleration, you've got this and this. Those are the two legs of a right triangle. You're going to use Pythagorean's theorem to figure out the total acceleration. Now, I'm going to go ahead and redraw this in the next board. I'm going to draw these tip to tail to give myself a direction here. So I'll start with AT, which is relatively small and goes that way, approximately. And then you've got A sub r, which is significantly bigger and goes inward. A sub r, okay? And I am trying to find the net total acceleration, okay? And I know these two values here are 4.5 and 19.4. Okay, so if I use Pythagorean's theorem on this, 4.5 squared, 19.4 squared, square root them, I get almost exactly 20. So the total acceleration is about 20 meters per second per second. Now, as always, you also should do an angle. Here you've got some options. I always personally measure my angle from the tangential direction. Okay, so to find that angle there, we'll call that theta. Theta is inverse tangent of opposite over adjacent, so 19.4 over 4.5. And if I do that, I'm going to get, I get about 77 degrees, okay? Now, when you say 77 degrees, it's good to describe like which way that is. So looking back at our original circle, if that's straight, that's which way he's going right now, which way his velocity is. His acceleration is 77 degrees inward from the tangential. Okay, so that's one way to say that. You could also say, let's see, if that angle is 34, or if that's 124, this here is 90 more than that. So 124 plus 90 is 214. And then you could add 77 more to that, and you could say, which will be roughly that way, that will tell you relative to the origin which way is the acceleration. But personally, I like to do it from the tangent, 77 degrees inward from straight ahead. Okay, if in other words if he's moving, his acceleration is 77 degrees to his left. Okay, so Hope that was helpful. A lot of kinematics. Also, you're doing rotational kinematics, and you're relating angular quantities to linear quantities. So for instance, angular velocity to tangential velocity, angular acceleration to linear acceleration. So I hope that was helpful, and thank you very much.